Okay.
It's like, look at this. They're solid. This is like such a good report. Wow. The first one's bad. This is like everything just being destroyed.
Oh, we have customers. Yes.
There's no applications. And I didn't want to put it in. That was Tim. Tim's good, but he makes strategic mistakes, right? That was a strategic mistake.
Can you read this?
Bigger.
Mamma mia. Va bene. Yes.
So I think you already noticed, but if there are questions or comments or anything from the audience, repeat it, because otherwise in the other room they don't hear it.
Okay. Please, if I don't, just like remind me, I might forget.
Usually I start waiting or something.
Okay.
So
Okay.
Alonso starts waiting over somebody.
Alright. Dai, io non capisco niente di quello che stanno facendo. Alonso, there's only one of these. There's no other color. Is there another color? No. Bah, dai, vabbè.
No, we have una preguntita. ¿Tú sabes para esa luz que está aquí que nos da como algo de ¿Cuál? Esa.
very perseverant. So I'm going to teach or talk about VMC, Variational Monte Carlo, and machine learning. Here's the outline of the talk. I'm going to do a kind of short recap of the lectures that we've had from Monday to Thursday and try to, see how it links with what I'm going to talk about today. And then I introduce Variational Monte Carlo, which is a quantum Monte Carlo method used basically to approximate quantities in the ground state of quantum many-body systems. And then I give a physical intuition behind the method. And I will discuss about the 3 main ingredients that you need to put together in order to cook up the method, right? First one is sampling. The other one is training or optimization. And then the choice of the wave function. And in these 3 ingredients, we are going to see where machine learning can be helpful. And then I will give a summary of the algorithm. All right. So I will start with the recap. So on the first day, Roger tried to convince you about, he talked to you about the fact that we are living in the big data area, right? Where now we have tons of data from which we can extract a lot of very useful information for different kind of things, right? Like speech recognition, using your Google Translate, image recognition, how you tag your friends on Facebook, right? Or maybe email suggestion, sometimes when you receive an email on Gmail, it suggests you how to answer it. So they use powerful machine learning techniques in order to either recommend a system or for speech recognition and this kind of a thing. And he mentioned the fact that in quantum mechanics, we also have a big data that comes from the wave function, basically. And how can we harness information from that big data using state-of-art machine learning techniques, right? And so in the first day, day 1, so not just about the big data in quantum mechanics. It's not just in quantum mechanics, also in classical statistical physics, right? You have configuration that can scale exponentially in the system size and how you can harness information from that. So day 1 we talk about the simulations of, I should write bigger. We talk about simulating classical many-body system. Where basically we look at a powerful method, the Metropolis Monte Carlo method, which is actually a generative kind of model to sample data, right? And we had a small tutorial on how we can generate data of the classical Ising model, right? Which is a classical many-body system. So already this time around we talk about generative model in machine learning, but Metropolis is a generative model that has been existing for decades. So on day 2, so here I should put generative model. Metropolis. So on day 2, we saw supervised learning, and from those who had a look on the bonus tutorial, we saw how using supervised learning, using this generative model, data generated by Metropolis Monte Carlo, we're able to characterize, phases of a classical many-body system. In that case, was the Ising model, right? So we use feed-forward neural networks to characterize phases of matter. Is it correct? I think so. And this was already an example on how we can apply machine learning techniques to problems in classical many-body system and get insight from those methods. So on day 3, day 2 to 3, okay, we saw unsupervised learning, where we basically use another powerful machine learning techniques to be able to visualize, phase transition in, classical data, right? Day 4, day 3 to 4, we saw a specific kind of generative model called the Resec-Boseman machine. And from this, we're able to approximate the underlying probability distribution from a data set. Okay. In the homework yesterday, we saw that data set was still something classical, but then Giacomo mentioned about the fact that we could use it also from quantum data. That could come either from doing some simulation of quantum Monte Carlo or directly from a quantum simulator. All right. And this could be used also to generate unseen data, or samples, generate. For the easing case, it will be configurations. And okay, in the case of a quantum case, represent a quantum many-body wave function. All right, so what these three, from day 2 till yesterday had in common is that they needed some input data on which they are applying machine learning techniques to get some insight about the phase transition, right? But now I'm going to talk about a different paradigm. Where we don't have no input data. And the question I'm trying to ask is, I focus just on quantum many-body system. So can I, without knowledge on some input data, still approximate well the quantum many-body wave function of an Hamiltonian? So I don't have any input data, which is maybe kind of sad, right? But we have the Hamiltonian, which is cool, right? All right, so which technique can we use to still be able to have a good approximation of the quantum many-body wave function of a quantum system? And so actually there is a very powerful technique that has been used for decades called Variational Monte Carlo that can do this. All right? So Variational Monte Carlo is a quantum Monte Carlo method that is used to approximate basically the wave function of quantum many-body system, and is interesting compared to other quantum Monte Carlo method in the sense that it gives you a functional form. It gives you an idea of what the functional form of the wave function can be, which the other quantum Monte Carlo methods don't. Right? And it has a lot of other interesting features that we're going to see. So this is kind of the problem formulation of variational Monte Carlo. Suppose we have an Hamiltonian H, okay? And this Hamiltonian H has eigenvalues En that you don't know, basically. So n goes from 1 to something. N equals to 0 is the ground state. And it has eigenstate phi n. All right. So what you are trying to do with variational Monte Carlo is this. Suppose that you have like a variational state psi that is parameterized with some a vector alpha, where alpha is made up of, let's say, p components. So what you are trying to do with variational Monte Carlo is to find the optimal vector or the optimal parameters alpha opt such that your variational wave function on the optimal parameter is more or less equals to the ground state wave function of your Hamiltonian.
More or less equal to what?
The ground state of the Hamiltonian H. So this is the problem formulation of variational Monte Carlo. Now, how do you solve this? In order to solve this, just a comment. So one thing that is interesting here is that this state can be anything you want. It can be complex, negative, whatsoever you want, you know. This is one feature that is also quite powerful with the variational Monte Carlo. And we're gonna, discuss about this later on. So in order to solve this, you need to define a metric such that when you somehow explore the space of the variational parameter, you are going to find the optimal variational parameter that is close to the ground state. So the question is, which metric do you choose to do that? And there is a very nice principle that helps us to choose that metric, and it's called the variational principle. All right. Can I erase this? Okay. All right. So, variational principle. All right, so let's say that we have our variational state. Okay, now I will replace this notation with alpha just to ease my derivation. So this means a set of variational parameters. Okay, so suppose I have my variational wave function. What I can do with this variational wave function, given an Hamiltonian H, and then the set of all the eigenstates of the Hamiltonian H, I can always expand this variational wave function on the eigenstates of the Hamiltonian H, right? So I can always do something like this. Okay? And now if I compute the expectation value of the Hamiltonian on this variational state, what do we have? Expectation value of my Hamiltonian. So I take this. So I replace this and this by this formula. You're going to have something like Nm, let's say Cn star Cm, and then Pn. All right. But since these are eigenstates of the Hamiltonian, because you have the value equation is this, so you can replace this by Nm star m Em, and then you have this conical delta, I think, yeah. And so this is going to give you sum over n, Cn star En. All right? So there's something that you notice immediately is that this quantity is always greater or equal to the ground state energy, right? So what does it tell us? It tells us that if I choose this as my metric, which in the jargon is called the variational energy, it acts as an upper bound to the ground state energy of the Hamiltonian H. So if I define my variational energy as expectation value of the Hamiltonian, okay, normalize, this is always greater or equal to the ground state. So I could use this somehow as a metric to be able to somehow search for these optimal parameters. How? Because the minimum value, so my optimal parameters will correspond to the minimum, kind of, hopefully, yeah, of my variational energy. So what I could do is somehow devise a search in the parameter space that minimizes the variational energy. And this will help me to kind of fix the parameters in my variational wave function. Okay. Questions? No question? No question. Okay, now I move on to the three ingredients that I mentioned that are primordial in order to do this kind of search. The first one is, let's say, sampling / computing observable. So there's something that you, for sure, for a typical problem, we don't have access to this. So we need to find another way to compute the variational energy, right? So imagine that you have an Hamiltonian of a system that could be spin systems. It could be, I don't know, like n particle interacting in, I don't know, some kind of either a potential or a box or whatever you want. So I can define X to be either like the configuration of a spin system is on a lattice, or the configuration of the n particles on the continuum. So let's just say that is any kind of configuration that characterizes your system. Okay, so the expectation value of any operator O can be computed as, so I take a generic operator, it could be the Hamiltonian. Okay. So I insert basically here and here a resolution of the identity. Okay. And then I obtain sum over x prime divided by some normalization curve, right? And if I define a quantity called a local quantity, which is equal to the sum over x prime phi alpha x prime I could recast my, can I write here? Expectation value of my operator. So sum over x, that local quantity at x. I mean, some normalization concept. Where, so this OX x prime is just matrix element of the operator x. So there's something that we observe immediately here. So for us to be able to estimate like the expectation value of any operator, we need to have a sum over all the configurations of your systems. Okay? And if say we are in a like spin system, like you can have spin up and spin down, this is the sum about like 2 to the n components. So that's like the curse of dimensionality Roger was talking about before. So you can do this, and I mean exactly for a large system size. You need to devise a way to estimate that integral or that sum. Okay? You might tell me that the local energy also have a sum over like an exponential amount of configurations, but you have this matrix element here, and typically this matrix element scale with the system size. So basically you have like, you can compute this in polynomial time. So this is not a bottleneck. The bottleneck is here. How do you estimate this quantum mechanical average? And as you can guess, you're going to use Monte Carlo. All right? So I would like to make an important remark. Oh, nice. Oh, okay. How does it work? Jesus Christ. Sorry. Okay. Okay. So, no, die. Let me hide here. I'm going to make an important remark about a very important property in variational Monte Carlo called the zero variance property. All right, so imagine that your variational state is equivalent to an eigenstate of the Hamiltonian. Okay? You notice that the local energy on the configuration, which, okay, here if I replace O by the Hamiltonian, you immediately see that the local energy is equal to the sum over x prime matrix element of the Hamiltonian. So, as I said, if it's a local Hamiltonian, it's scaled polynomially. X prime divided by, okay? This, you can rewrite it as this. It's better for visualization. How do you say it? I mean, it's better to understand the derivation. To write this as this, okay? And you see that if the if the variational state is equal to an eigenstate of an Hamiltonian, you have this. And H, like acting on the eigenstate, gives you the eigenvalue and the eigenstate, right? So you can have something like this. So you see that the local energy is not only is independent on the configuration at which you are, but is exactly an eigen value of the Hamiltonian, right? And by the fact that it's an eigenvalue of the Hamiltonian, implies that its variance is actually 0. But there's something even that is more fun, right? Is that if you compute basically the variance of the Hamiltonian on your variational state, okay, let's say that I kind of do something like this. I put here a resolution of the identity. I'm going to have sum over x, then you have this bar h, x, x, h. Okay, I have some normalization that you don't matter care very much. Okay, and then you can, so if here say 1 equals to, like, you divide and then you multiply by something like this, right? Okay, you do this here and then you do it here. You can show that this is equal to the local energy squared on the variational wave function squared, okay, divided by basically the variational wave function squared. Okay, and this you can immediately see that gives you some the variance of the local energy. So you see that the variance of this, stochastic variable that is called the local energy is exactly the variance, the quantum mechanical variance of your Hamiltonian on your variational state. So it tells you that the lower the variance of the local energy is, the lower is the variance of the Hamiltonian on that variational state. So this is like another metric that you can use when you are optimizing your variational parameter to ascertain that, okay, I'm going towards an eigenstate. Okay, here it can be any kind of eigenstate. But from what I told you before, the variational principle, from the fact that, okay, I remove it, the variational energy is an upper bound to the ground state energy, the two combined together somehow gives you a strong assurance that, you are basically updating your variational parameters towards the ground state wave function of the Hamiltonian. Okay? And it's also some just technical, comments. So it means that the closer your variational wave function is to an eigenstate, the less statistical fluctuations you have, and the less is the computational burden that you have. All right. Questions? No question. Okay, so coming back to what I was mentioning about computing observables. So the expectation value, oh, nice. Oh, sorry. Oops. Sorry. So, oh yeah. So the expectation value of an observable on the variational state, okay, which is, you can replace as the expectation value of a local energy, like this. So what we do in variational Monte Carlo is that, can you see it? The quantum mechanical expectation value is approximated with some statistical, average, whereby okay, let me do something. So this is just saying that you approximate with some statistical average over some probability distribution, right? Which I will tell you in a minute what it is. So for example, the expectation value of a local quantity is approximated as 1 over ns, which is the number of samples, sum of n going from 1 to ns of xn, okay, where xn are drawn. How do I drawn? From a probability distribution, Px of n, which is basically the square okay. I will explain later. Ns is finite number. Finite is important because this is where you basically reduce exponential complexity to something that is polynomial or scalable. And I will tell you in a minute why you can do that. Finite number of uncorrelated samples related. Alright, so what have we done here? What we've done here is that we need to estimate a quantum mechanical probability distribution. We need to do the sum over all the 2 to the n for a spin system possible configuration of the system. But not all the configuration of the system matter. The configuration of the system matters. So you can devise a way of taking the sum over the configuration of the system that have more weight, right? And this is where important sampling comes in. And so you can devise a Markov chain so that the equilibrium distribution of the Markov chain gives you configurations that are the most relevant, the important configurations. And you do this by building a Markov process where the equilibrium distribution of your Markov process is given by this probability distribution. And if your Markov process is, of course, ergodic and memoryless, so this is where the uncorrelated comes from, then you are kind of sure that you can compress the exponential complexity to something that is polynomial, and you can have estimates of the observables that are quite good. All right? Questions? No question. Where am I? So I'm going to comment towards the end when we talk about the choice of the wave function, about the importance of the samples to be uncorrelated. Maybe I can just do a small sketch here. So typically when you compute observables in Monte Carlo, right, you have you have this plot. Let's say this is the number of Monte Carlo steps, and then on the y-axis you have some observable that you want to compute. And during the simulation, your simulation usually does something like that, and then it starts fluctuating. Okay. This time you generally throw it away because it's the time it takes for your simulation to converge, right? And then at equilibrium, you have the way in which you sample the average of the quantity is that, so here you have kind of your equilibrium time, and then here you have other stuff that they call like some correlation time, So what does it mean? It means that at this Monte Carlo step, let's say you compute, like the observable here, you wait some correlation time, you compute again the observable here and then here, and then you do the sum. That will give you the estimate of the average. Why do you do this? You do this because when you build your Markov process, the Markov property tells you that the probability for you to be at the configuration X has to be equal to the sum of all the possible states, the transition probability to go from X prime to X, and then the probability to be at X prime. Okay? And typically this transition probability depends only on the previous state. So it doesn't depend on all the other states in which you have. That's, the property of the Markov process that needs to be like memoryless. And so for you to remove correlations, because the way in which you build a Markov process is, if you are at the configuration 1, and then let's say you do a spin flip, you go at configuration 2, you do maybe another spin flip, configuration 3, and maybe you do a spin flip, it's not accepted, you remain there, and then you go configuration 4, configuration 5. There is some level of correlation between this and this. Maybe at this state, maybe you still have some memory of the state x1. So you need to perform metropolis for a certain number of time that I will call maybe correlation time to completely remove the memory of the previous state. That is the reason why, you need to sample quantities, after some correlation time, and this you are sure that you're going to generate uncorrelated sample. So there's a lot of different techniques that people use, like binning techniques and jackknife methods. But so basically the idea is that with a metropolis Monte Carlo, at each Monte Carlo step, so between subsequent Monte Carlo steps, you generate uncorrelated samples. You generate correlated samples, sorry, and you need to wait for a certain time, correlation time, let's say, to completely remove the memory of that. And I'm going to mention about, a specific choice of a variational wave function that is based on some fancy neural network that basically at every Monte Carlo step gives you directly uncorrelated sample. And you can imagine that this is going to speed a lot, the simulation of the Monte Carlo, because you will not need to wait for very long Monte Carlo time to take averages over the quantities. All right? Okay, so now I will give briefly the algorithm that you use for metropolis in this setting, VMC. Can you see here? I guess not enough light. This is Monte Carlo. Okay. So what you will do is you will pick maybe a state randomly. Or you initialize your state randomly. And then you repeat this procedure a certain number of times. You propose a move to go from, okay, let me just put like this, from X to X prime. And then you accept the move. With, I think Roger explained it very well. For an acceptance probability to go from X to X prime, which is the minimum between 1. Here you just write a generalized acceptance rate. Okay, well P, so if So this is the transition probability distribution that you use in building your Markov process. And typically, just to remind you, the transition probability is divided into probability to propose a move times the probability to accept that move. Okay. So this is a proposal probability. If it's symmetric, like flipping a spin at random, you're just going to have the ratio between the square of the wave function. So you accept the move with that, and you do this until you are, kind of satisfied of certain convergence. Right? Here you can have, some fancy move like flip a group of spin or flip a spin flip to help you be more ergodic, but typically, just a spin flip is fine for spin systems, typically. So now I will make some comments about this acceptance probability in the metropolis. Okay. So as I mentioned, so you can see that acceptance probability depends on the probability to be in a state that is basically related to the square of the wave function. So in the beginning, I was telling you that, your choice of the variational wave function could be even complex. Why? Because when you define, you take the absolute value score of the wave function is positive. So even if your wave function is negative, complex, you can still build a Markov process to, estimate observables. And this is quite important because this is sign problem free. So QMC is the only Monte Carlo, VMC is the only Monte Carlo method that does not have the sign problem. In this sense, I see Giacomo looking at me like, what is in this sense, but of course the sign problem pops up somewhere else in estimating off-diagonal observables. Have I moved it? Where is it? So let's say when you want to compute the local energy, you have this. So x prime. So here, if you don't have the correct sign structure of your variational wave function, you basically have wrong estimate of your local energy, which means wrong estimate of your, of the energy, the average energy of the Hamiltonian. So even though there's no sign problem, it doesn't guarantee you that you find things that are correct. So still, you will need to have the sign structure encoded somehow in the Hamiltonian. Okay. So, yes. Question before I move to the second ingredient? No question. So now we have the first ingredient. We know how to compute observables in the VMC setting. Can I erase here? Or which one I have to? I don't remember. This one is this one. So the next ingredient for our recipe is actually how do you optimize the variational wave function, right? So recall, I told you that, what did I tell you? Okay, that the aim of VMC is to find an optimal set of parameters such that the variational energy is minimum. Right? So one thing you could directly imagine is that we could update the variational parameters following the gradient of the variational energy. And a very popular method to do so is called stochastic gradient descent, which we have already heard. So let's say that alpha is a set of, of P variational parameters. Let me write it this way. Alpha is a set of P variational parameters. The way in which I upgrade one of those variational parameters that I call alpha n. So alpha n at a kind of different step. Alpha n as a previous step minus some mu that is we call the learning rate. The derivative of the variational energy with respect to that variational parameter. So in doing so, you basically follow the gradient of the variational energy with respect to that variational parameter. So I just make a small comment about the learning rate because a lot of people ask me about that question. So imagine that your parameter space is something like this, right? You want to find the global minimum because this will correspond to the set of your the set of your optimal parameters, okay? And let's say you are somewhere here. So if you follow the gradient, if mu is large, right? So you'll be going like very large step inside here, and then you'll be kicking like in a very strange way because mu is large.
Estelle?
Yes.
We have a question from the other room.
Oh yeah. Yes. Whoa, I only have 10 minutes? Mamma mia. Okay, I'm almost through. So, yeah.
At the beginning, you are generating samples. You have a time series of samples of the states. Before computing any other,
You have to come back, yes.
how do you compute actually the correlation time? Because at the beginning, you are generating samples. You have a time series of samples of the states. So before computing any average, you have to filter by the correlation time. So how do you compute the correlation time from the samples?
Oh, so his question is like, in the Monte Carlo setting, you have this kind of, so you have the observable that goes in this, you write in this fashion, with respect to the Monte Carlo step. So when you want to compute observable, how do you know either the correlation time and I guess probably the equilibration time also, for you to be able to take averages correctly? So there's a lot of different ways in which you can do that. Either you run small simulations and then you see basically how, what is the trend, and then you just remove all the samples. So you deal with the equilibration time. And then the correlation time, what you can do is typically you use the binning technique, whereby you compute basically the fluctuation of your quantity. So let's say, I think you can even use it without removing the equilibration time. So let's say you have this time series that is this long. You can decide to divide it in like equidistant number of bins, right? And then you basically like take the averages of your quantities for each bin, and you plot the fluctuations of that quantity with respect to the number of bins. And you are going to see something that goes like that. So typically, when it's flattening, so typically this will tell you the size of the bin that is enough for you to have removed all the correlation in your system. So this is called a binning technique. Right? Well, this is one of the ways you basically deal with the correlation time. Another thing, you can compute autocorrelation functions, and then from there you can have an idea of like how your observable relaxes. Another thing is, there are some methods like the jackknife method. So either you compute autocorrelation function, or you use some, you do some post-processing of the data using the binning technique. I don't know whether that answers the question. Another question? Yes?
When you were explaining the zero variance property, you mentioned that there's
Which property?
the zero variance.
Yeah, okay.
You mentioned that there's a quantity that gives us an indicative of how close we are to the ground state, right? No? Or how
Close we are to an eigenstate.
okay.
Okay. Yeah. Now the variational principle tells you that, if you minimize it, then it gives you a lower bound to the ground state energy. So the two together combined makes you something more powerful, to go towards the ground state, yeah.
Is there like any way to use that to improve the optimizer?
Oh yeah, so some people use, actually instead of oh, sorry. So the question, what was the question? So, wait guys, let me think. Yeah, so the question was about the zero variance property. So his first question was whether the variance of the local energy is related to just basically the variance of the Hamiltonian for the ground state. But the answer is no, it's for any eigenstate. So the variance of the local energy is going to be zero if it's equal to any eigenstate of the Hamiltonian. Okay. Now he asked, the second question was, can we use the zero variance property somehow to train the network? Is it?
To improve the behavior of the optimizer.
Yeah, so to do optimization. Okay, now I'm talking about network because I assume that the variational wave function is a neural network, but it could be any kind of thing. So yeah, to do the optimization of the variational parameter, the answer is yes, because if you meet at least the variance gives you a clear lower bound of whether you have still reached an eigenstate, because the variance is zero for an eigenstate. So you can minimize the variance and end up in an eigenstate. I'm not so sure about the ground state, right? And people have shown that doing variance minimization, you obtain wave functions that do not give you correct energies for off-diagonal observer. So and then you can use, some people use techniques where you at the same time minimize the variance and then the variational energy, yeah. Right. So I was trying to explain the effects of the learning rate. So here I was saying that if the learning rate is large, you are basically not optimizing anything, right? But suppose the learning rate is small. So suppose you are here, and then the learning rate is very small. The next step takes you here, and then the next step takes you here, and you take forever to converge to here. So if your learning state the learning rate is very small, you need a large number of optimization steps. So you need to find something in between. So this is an hyperparameter that you play with. The same thing like in machine learning techniques. Okay. So yeah, so this is a stochastic gradient descent. Oh, sorry. It's not true. This is gradient descent. I tried. There's nothing stochastic about it yet. All right. So how do you estimate the derivative of the variational energy with respect to any variational parameter? One thing that you are going to do in today's tutorial is to do exact differentiation. But this is possible only for very simple system like the harmonic oscillator. So typically you cannot do that, and actually it's not even advisable. And I asked you the tutorial why it's not advisable to use the exact gradient to do optimization. All right. Another thing you could do is to use some numerical techniques to estimate the derivative of the variational energy, because you know that if you have a function, you can estimate it like, I don't know, something like that, right? But somebody can tell me why this is not advisable to do this kind of finite difference, Taylor expansion kind of thing? in this to estimate like the derivative of the variational energy? Why?
Rounding errors?
Sorry?
Rounding errors?
Rounding errors? Not far from that. Yes?
You need as many divided differences as you have variables. By the way, I've written a whole book on why exact differentiation is possible, so you can't get support on the claim that exact differentiation, whatever exactly means.
The claim is this is a stochastic variable. It's not like, I mean, any kind of function, I mean, some polynomial you can think of. It's a stochastic variable. And then this kind of differential of stochastic variable varies a lot. So basically you are going nowhere with.
But this is being done, for example, in option pricing, where you have Monte Carlo methods, and people do Monte Carlo methods to get the corresponding derivatives. Fixing the random variables and doing essentially backpropagation.
Fixing the random variable. Well, we can talk about that a bit later, but now I'm going to talk about how you can use Monte Carlo actually to estimate this derivative. I'm going to talk about how you can use Monte Carlo still to estimate the derivative of the variational energy.
Can be.
But I don't think this finite difference stuff is going to work because I mean, it's going to be too crazy. It's kind of derivative. All right, so what you do up to now, I mean, there's not really something like stochastic. I'm just going to tell you about how you evaluate the derivative of variational energy. If I find my note, okay. So the derivative of the variational energy over, let's say, one variational parameter is going to be the derivative with respect to this. Okay? So if you, I'm not going to do the whole derivation, I'm just going to kind of give you a flavor. So if you take this derivative inside and then you perform all the derivation and everything goes on well, hopefully, you're going to find this 2 times, this stands for real, the quantum expectation value, the local energy on this configuration, times a force, kind of pseudo force on the variational parameter that I will define in a minute. Where this, yes. Where f of n is nothing but 1 alpha n. Okay, and this is exact. So this is no approximation. All right, but now the approximation comes because we cannot. So these are quantum mechanical expectation values, and as I said, we cannot compute them exactly because we have to sum over 2 to the n configuration. So you replace this by the statistical averages that you compute with Monte Carlo, basically. And so the derivative will not be exactly the derivative. Let's say there will be approximates of the derivative. And so you're going to have fluctuation that brings the stochasticity in the stochastic gradient descent. And so when you estimate the derivative of the variational wave function by replacing the quantum mechanical expectation value by the statistical one, then you obtain an update that is now stochastic gradient descent. And I'm going to make a correlation with what you already saw in machine learning, because in machine learning, this so in machine learning, when they use stochastic gradient descent, the gradient of a cost function is estimated using so typically you do a sum over the whole sample, but they don't do the sum over the whole sample because it's like, if the sample is like too large, you don't do it. They take a subset of the sample that they call like mini batches. And so the derivative taken on those mini batches gives you the stochastic gradient descent that they have in machine learning. Okay? And then I talk very fast about a more sophisticated way of updating your variational parameter, which is stochastic reconfiguration, where basically you build a covariance matrix made up of correlation between the pseudo forces on your variational function, variational parameters. So you build the famous X matrix, which is nothing that how much time do I have? Typically I'm done.
But I mean, you still have the other row, no?
Yeah. Okay, let me go fast. No, I have tutorial. I can mix both of them. Okay, let me be more so the star is the complex conjugate. Okay. And the way in which the parameters are updated. And this is still like, both of these are estimated stochastically. So the idea also, if this matrix is identity matrix, you recover the stochastic gradient descent, let's say. But somehow you renormalize, this matrix applies this like to the gradient of the variational wave function, kind of affect the way in which the variational parameters are optimized by changing more the parameters that changing in a smart way the parameters that matter the most, let's say in the variational wave function. So that's why this technique is quite powerful and very fast to optimize also. So I did the derivation of this very carefully. So you can check a tutorial. So there are some notes online. I don't have time to derive it here now. So if you go on this website, you check the tutorial on VMC and machine learning. There are other nice tutorials also. So this was a conference we had in Santa Barbara in KITP a couple of months ago. You can have all the derivations. So basically, one thing that you can see is that you can derive this by supposing that between subsequent updates of your variational parameters, the wave function, like the normalized variational state doesn't change much, right? So if you impose this constraint on the way in which you explore the landscape of the parameters, you're going to find exactly this equation. So you can check the notes. All right, so I'm going to move to the third ingredient that we need to do VMC. The choice of the variational wave function, whatever it is. So traditionally, so up to now, except for a brief comment, there is nothing in the VMC derivation that is related to neural networks, let's say, okay? Because this is something that people are routinely be using in condensed matter and statistical physics. So they have developed a zoo of variational wave functions that are basically super well crafted to the problem Hamiltonian that they are looking at, okay? So among which you have things like Jastrow wave function that takes into account correlation between, let's say, spin variables and stuff like that, or like positions in space of some particles. You have like things like RVB, which is like a variational wave function inspired by the BCS state. And then you have like many other. I think on Monday we had a talk where we had an NPS as a variational wave function. Right. So the question that I want to make is, could we design a variational wave function whereby we don't use too much the knowledge we have about the Hamiltonian in such a way that somehow our variational wave function is able to harness the correlations that are, in the model? Is it possible to do that? And there is a theorem called the Kolmogorov. Arnold representation theorem. That tells us that every multivariate continuous function can be represented as a superposition of continuous functions of two variables. And the mathematical form says that if you have a function f(x) Alright, so you only need to fix two continuous functions in order to represent basically any other like multivariate continuous function. And based on this theorem, people have thought that, oh, actually we can have some inspiration from nature about how we can find a functional form that obeys this theorem. And this is biological neural networks, right? In the sense that this part could be replaced by, imagine that you have like some kind of neurons. Okay, now it's kind of artificial neurons, but you could do it with biological neurons. And then it's outputting some things here. Okay, and then here you have some weight 1, weight 2, weight 3. Okay, and then you can define some Z, which is basically the sum over the weight times the unit. I don't know where I have to put some T there. Maybe some bias that gives the threshold. So you have some kind of like linear combination of the weights of the bias and the entries, which could represent this part of the function. And then you need to find a continuous function, which in this case is the activation function. It could be like sigmoid of Z. And so this is basically this. And you can use it as a building block somehow to build a function that can capture by itself kind of all the correlations of the underlying model that you're looking at. And so there's this very famous paper that I guess almost everybody knows, yeah, by Carlo and Troyer in 2017 that use this kind of idea in order to find a generic variational wave function that can capture, most of the correlation of a quantum many-body system without being explicitly tailored, okay? And this is the resisted Boltzmann machine, based on the resisted Boltzmann machine that we saw extensively, okay? So the idea is that you have, I'm sure that many of you already seen this kind of plot. So this is a visible layer made up of configuration of a spin system. And then you have hidden layers, M of them. And then you have this kind of connections, intra-layer connection, no inter-layer connection. Right? So you can use this kind of energy-based model to build a variational wave function where you average out all the hidden variables. Then you have exponential of sum of j going from 1 to the number of visible spins, some biases, plus the sum over I from number of hidden neurons, biases of the hidden neuron. Oops. Okay. And then you have the connections in between visible and hidden neurons. Alright. I think we already saw that, right? And Giacomo showed you that, you can you can put this exponential, so I don't want to write it. So you can estimate it as the product. What is I? In the hidden neurons of exponential. So here if you assume, okay, no, whatever, log cosh All right. So what you can spot directly is that, like Giacomo was mentioning yesterday, here you get, all correlations between visible spin at all orders, kind of. And by learning these parameters, somehow you are able to capture the underlying correlation in your model. So this is somehow where the power of, having a representation of the variational wave function by the, let's say, Boltzmann machine comes. Another question?
Yeah.
Yes.
So the parameters here are complex, right?
They could be. They could be. Why not? Yeah. All right. So what was I saying? Yeah, and then you could, people have used other kind of neural networks to represent the variational wave function. So the idea is, can we use a generic wave function that is not highly tailored to the Hamiltonian, and just by a learning procedure, capture directly like the information, the correlation among the data. And people have found it to be quite powerful. So I end up by mentioning a very recent paper. So up to February, beginning of February, if you ask me, how can VMC, Variational Monte Carlo, beneficiate from machine learning, I will just tell you, from having a powerful, ansatz that has that is representative enough, that is a powerful variational wave function that can capture the correlation of a ground state wave function. So just from the representation of it. But now, like 11th of February, there's been a new paper by Carlo and other friends that basically use another kind of, neural network called deep autoregressive neural network, in order not only to have a strong representation of the variational wave function, but also help in the optimization and in the sampling of observables. Because like I told you before, one of the bottleneck of VMC is the fact that you have to build a Markov chain. And by building a Markov chain, you need to make sure that you have uncorrelated samples, which means that you need to wait a certain number of time for the correlation to be gone in your Markov chain. Because between two Monte Carlo steps, you have correlated samples. So they basically built this kind of variational wave function whereby at each Monte Carlo step, they can generate uncorrelated samples. And by doing this, they have two main advantages. Okay? So let me write it down. February. You can check the paper, I wrote it somewhere. It's on archive. Okay. Okay. It's based upon deep and it deals with two problems. The first one is correlated samples, and then it speeds up the algorithm. And the second point is that suppose that you had a deep neural network as a variational wave function, or maybe a research Boltzmann machine with a large number of hidden neurons. So you know that as you scale the number of hidden neurons, the more powerful is the variational wave function to capture, properties of the ground state. But the more difficult is it for you to simulate it, right? So it means that you have a constraint on the number of hidden neurons and the number of layers you can add in the variational wave function that is based on the neural network. But by by having this kind of highly craft variational wave function, since you no longer have to wait for your samples to be uncorrelated, you can basically, scale up the number of hidden neurons or the number of layers. So it increases the representational power of your variational wave function. Okay? Which is cool, I think. All right. So I will give a summary of the algorithm, the VMC algorithm, how you will code it. No. So first, choose a smart variational wave function. Okay. Since we like machine learning, we take a neural network, right? Okay. Which depends on a certain number of variational parameters. By the way, for a neural network, this alpha will be the set of weights and biases. Okay. So after you've chosen it, you need to evaluate the variational energy, and after that you vary the alpha parameters according to some minimization scheme. Minimization scheme. So for a neural network, that's the part you call training. And as we saw, you could use stochastic gradient descent, stochastic reconfiguration, some other fancy stuff like momentum method, Adam method, whatever you want. Okay? Train your neural network. And then you stop until you reach some convergence that you define. Convergence criteria. Alright, so that's the VMC algorithm, and sorry for the time, I took too much time. I'm done. Any questions? I saw a hand somewhere. Yes?
We can still poly in this overfitting the data with all these probabilistic overfitting the data that we want to approximate in the supervised learning, for example.
Where are we going? Oh, sorry. So the question is whether we could still have overfitting of the data we want to represent. Can we have overfitting? Let me think. Yeah, I think you could have overfitting. No? You couldn't? Let me see. Anything.
I guess one comment could be that so when you do a gradient step,
Yeah.
in the minimization procedure, you only use the data set once, right? You compute the gradient with the generated data set,
Yeah.
you use it once, right? Like, so you don't reuse this. So I don't think this sounds like overfitting.
So what if you have a large number of parameters and your data set is small?
But there's no data set, right?
Well, so there's no data set per se, but the number of Monte Carlo samples that you use to estimate observable at that gradient set, at that gradient step, that is your data set. Mm-hmm. Right?
But you use it only once.
Yeah, you use it only once. Mm-hmm. So could we talk about overfitting for one gradient step? I don't know. I don't know. I have to think about that. I don't know. Fitting. Another question?
When you use the Morgorov representation is to the two variable function
is to the
representation only in two variables.
Yeah.
Is with respect to the weights and biases, or in the what? Because you mentioned that you use the theorem for a representation of two variables. Because the Kolmogorov also goes to the one variable model.
So
the question is why you said two variables. With respect to your model, what are these two variables?
Oh, so yeah, thanks. So when you use the Kolmogorov theorem, you need two variables. And what are the two variables in the neural network? Is it what you are talking about?
But it's also true with just one variable. Yeah. Non-linear functions and the additions is enough.
Yeah, so I think what is important is actually the two continuous functions. I mean, the one that gives you the linear combination between the weight and the biases, and then the activation function. So now the two variables, let me think. 6. I mean, I would say that one variable is, so should I write this? I mean, this is how I would think about that. Like one variable to be like the input state of your previous neuron, and the other one to be like the linear combination of it and the biases. Yeah. I mean, the strength of the theorem comes mostly like from these two functions that need to be continuous. Yeah, but then for a neural network, I could imagine this to be like the input of one neurons, and then this to be like the linear combination of it before you have your activation function. Yeah, right. Oh, you don't agree.